So this term you have only the mu naught. Okay, so this is the wave equations in terms of E and P. Right? Okay, so just now I show the things that are used. All right, so this is the wave equation. And then we go back to the papers because we want to derive the results in paper. So the paper, we have this. We have this and then blah, 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 and then you have these results. The author did not show the steps, but he showed the results. You want to obtain these results, equation 3, yeah? So see how we do. Okay, so from the beginning, the real view. Okay, so we have done this before also. Okay, this one we have done this last semester. Okay, from our Duffing equation of motion, we have this, and then we get this is just to rearrange. Okay, to rearrange the terms. This one, I think you have no problem, right? I think I try to find, recall you. This is your file that you sent just now. See whether you managed to type it or not. Okay, you didn't type the results. Okay, so you have this Duffing equation, this green one. Okay, when you work it out and all these things, and then you have these results. P double dot. So this is your P double dot. This is gamma P dot. This is your gamma P dot. You have this constant because of the Duffing equations. Okay, the Duffing equation is in terms of x, and then you want to write in terms of p. So that's why you have all these constant m over e around. But I do not copy paste here. Yeah, right. So it is in equation 2. Can you follow what I say? Okay, so the equation here is nothing new. This equation is nothing new, but I just don't want to write the del square p over del p square. So this one I write into p double dot. This one is p dot. And then this divergence of b, divergence of b, okay, is this. Okay, divergence of b is this. Because b equals to half kappa x squared plus 1 over 4 beta prime x to the power of 4. And after taking the gradients, you have this. Okay, so this term is come from this term. Okay, the minus, you move to the left, you get the positive. Okay, so that's why you have the positive. And then this one is like, is in here. Okay, so this equation and this equation of the paper exactly the same. Okay, and after this, you want to reproduce the results here. Okay, here you didn't see any gamma omega, but here you see it is already in terms of omega. All right, this delta also in terms of omega means that you already take the time derivative of this and this. Okay, how to take the time derivative? We have to use the time derivative of P due to application of E. Okay, this E here has the Z dependence and T dependence. So we look at the time dependence first, the T. Okay, so this one, you can think of the field E and the field P are separable. Means that this term depends on two variables, Z and T. You can write it as a function of Z multiplied with function of T. So if we do this consideration, it becomes half Pz multiplied with this function in terms of exponent minus I omega t. So here, usually we don't want to change it, but it should be the new symbol. This P and this P should not be the same because this is simply depends on Z, but this is depend on Z and T. So better I should call this one some other symbols, but to make my life easy, I call it the same things. So understand this. And of course, you must have the plus CC. So in any direction, you must always use the complex notation. And later on, we ignore the complex part. We ignore the conjugate part. So we write, this field is real, but in complex notation, we write this complex field plus the conjugate. Okay, so this one break into two parts, Z dependence and T dependence. Likewise, the E also can be broken down into EZ and function of T. All right, so after we have this consideration, we plug the P like this into here, ignoring the CC. Because when you put like this, once you solve the complex, then you automatically can get the CC. Okay, so when we plug into the field there, let me see. Okay, so I think last time I do point out some things. Okay, there are 4 over 3 over 4 here. Sorry, there are 3 over 4 here. And I think I do show that it should be 3 over 4 because based on the Duffy oscillator, just the x. And after this, we consider the powers of 3. Then we have the 3 over 4. Because of when you take this cube, the P, you have 2 terms. If you take the powers of 3, you have 8 terms. Okay, and then 6 terms of it will contribute to the fundamental frequency. Means that if you expand this by using this, then you have 8 terms. You have 6 terms which carry the omega. There's 2 terms related to 3 omega. So we just want the, no, I think not, we have 8 terms. 4 are conjugate, we ignore the conjugate. So if we consider the conjugate, then you have 6 terms. But if we consider only the complex, then we have only 3 terms. 3 terms out of the 4 real terms carry the omega. So that's why we have this. So this one is okay. So here we already consider the cube into here. Okay, so and before we do the time derivative, the steps here is just to simplify the constant. Because this term carry this, we don't want to see this constant in front of the highest time derivative. we multiply every term with this